been talking about the fact that a slope is a derivative and a derivative is a slope. A derivative gives you the formula for computing slopes at any point. A couple things I want to hit on in section 1.4, and then I'd really like to even get into section 1.5 today. Whoa. Really? Okay, we've already laid a lot of the groundwork for section 1.4. Early on, I try to provide information multiple times that you're going to run into later, so that when we actually hit it, you've heard it about 17, 20, 25 times, and it's finally starting to get to be a thought that you're comfortable with. Okay? I'm not just repeating myself because I forgot I said it. I understand these ideas are new. They take some time. We've been working with average rate of change. Okay? That's what was going on in section 1.2. And section 1.3 was average rate of change. And with the average rate of change, if you have some function, and let's say the function does something like this, we'll call this f of x, or another name for it would be y, because y and f of x mean the same thing, don't they? Okay? When we're doing average rate of change, we might have a point over here that we're interested in. To get the average rate of change, you choose a second point. We might start over here, and the average rate of change is the slope of the line segment formed by those 2 points, isn't it? To get a better estimate, we then take this second point and we slide it over here and compute the slope there. And you know this routine now, don't you? I mean, come on, Chuck, give me something new. I know this. Okay, and we keep sliding that point in. As you slide the point in, you get closer and closer to the point of interest. And if we took an electron microscope and enlarged this, the way the calculus would work, okay, if we're super enlarged, is we would have our point of interest there, and we would slide the other point really close, and what we would be looking at would be the line segment connecting those 2 points. The distance between the points approaches what? 0, doesn't it? Okay? If you want to know what the slope is at any one point, and remember, can we really do the slope at one point? Okay, so if we wanted to know what the slope at one point is, we just take 2 points, slide it in really, 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 really close, keeping 2 distinct points, because you can't do a slope without 2 points. Okay? And what we're really doing is the limit as h goes to 0, f of x plus h minus f of x over h. That should look really familiar to you. We were working with some of these last week. We were talking about how you can get equations for derivatives using this last week. Okay, we're going to run through another 1 or 2 of them today, but realize this is the name of the game. Right there is the whole game. That's going to drive everything with derivatives. Very important when you are doing a limit. We got to reach way back there now in chapter 1 to where we were talking about how limits work. For this limit to be defined, as you're coming in from the left and the right, you have to approach what? The same point, don't you? If this limit exists, that means a couple of things. It means, first off, the limit as h approaches 0 from the left equals the limit as h approaches whatever it is from the right. Does that look familiar? Which is why I was just mentioning about if you come in from the left and the right, it's got to look like you're headed to one specific point. The second thing is the function at whatever your value of interest is. So let's say this is the point x equals a, and that's what we're interested in getting a tangent line at, has to be equal to some particular value. I'm going to call it k. And the third thing it has to be true is the limit as h approaches 0 has to equal whatever that value is, has to be k. What this says is, as you're coming in from the left, it looks like we're headed to, Johnny Rocket. Is Johnny Rocket still over at Kenwood Mall? I don't know. I've not been over there in years. Okay. What's a good restaurant over there? McDonald's. Okay. From the left, it looks like we're going to McDonald's. If we're coming from the right, it looks like we're headed to McDonald's. When we pull in a driveway, we're actually at McDonald's. The first thing, 1 on that list, from the left and the right, it looks like we're headed to McDonald's. 2, when we pull in the driveway, we're at McDonald's. 3, when we're headed for the driveway, it looks like we're going to McDonald's. And when we pull in the driveway, we are at McDonald's, and it all works out to be the same. This is really important. If these 3 things are not happening, you can't do a derivative. You can't. If these 3 things are not happening, okay, there are some issues, okay? And what it winds up meaning is, if those 3 things aren't happening, you can't do the limit, can't you? And if you can't do the limit, can you get the derivative? No. There are places where derivatives do not exist. There are going to be problems this year where you're asked, compute the derivative at some point. Well, it doesn't exist there. Don't spend the next 2 weeks romping around these woods looking for Bigfoot. Why wouldn't you spend 2 weeks looking around in these woods here for Bigfoot? Well, first off, it's not enough room for Bigfoot, is it? What's the other problem? Odds are Bigfoot, this may crush some of you, Bigfoot doesn't exist. Don't bother spending your time looking for things that don't exist. The first thing you've got to do is determine if it even exists. And there are going to be problems where it doesn't exist at a location. You explain why it doesn't exist and move on. What do these points look like? Okay, derivatives do not exist. If, 1, you're at a corner. A corner, what's that look like on a graph? Okay, this can also be a cusp. On a graph, it's going to look something like this. Or it might go like that. Either of those is a problem. The first of them, the lines coming up to that point are both curved. That is called a cusp. The second one, the lines coming up to it are supposed to be straight lines. That's a corner. Well, what's wrong with having a derivative there? Well, the catch is, remember, we're looking for tangent lines, aren't we? Okay? Going back to our original graph, we can do tangent lines. A tangent line is a line that intersects the graph in how many locations? 1 point, and 1 point only. And if we're looking for derivatives, how many tangent lines can you have at a specific location? 1. There is just 1 derivative at a location. Does that make sense? If we look at this cusp, that's a tangent line, isn't it? It only touches the graph at 1 location. Okay. But the problem comes in at this cusp. That's a tangent line, isn't it? At the same point? That's tangent line at the same point. That's tangent line at the same point. How many tangent lines are there at that cusp? There are an infinite same thing happens at the corner, doesn't it? Do you see that you can get an infinite number of different tangent lines at that corner? Derivatives do not exist if you're at a corner. Okay, derivatives do not exist if you're at a cusp. Second thing, derivatives do not exist if you're at a point of discontinuity. Well, wait a minute. If you're at a point of discontinuity, is the limit going to exist? Okay, yeah, we run into a problem there. So a discontinuity might look something like this. So you come on up to here, and there's this. Do you buy that that's a discontinuity? Well, the first problem is, does your limit from the left equal the same value as your limit from the right? And the answer is no, it does not. Because if you're coming in from the left, it looks like you're headed to this value, doesn't it? If you're coming in from the right, I'm not sure that's going to show up. Let's try that. If you're coming in from the right, looks like you're headed to that point. Your left-hand limit and your right-hand limit are not equal. And if the left and the right-hand limit do not equal the same value, does the limit exist? No. You're done. You can't do the derivative. Well, if I can't do the derivative, Chuck, what am I supposed to say? Just say the derivative does not exist because there is a discontinuity at the point of interest. Now, be careful, because you can have a discontinuity, okay, and still have a derivative. Like what? Well, suppose we're interested in this point way over here. The discontinuity is this point. I'm making up some number 2. But if we're interested in -4, can we compute the derivative at -4? It's continuous there, isn't it? Even there's a discontinuity somewhere within the domain of the function. This point of discontinuity is not at a location that's of concern to us. Okay. A couple days ago, what happened down around Houston, Texas? Anybody hear about that? Hit by a big storm. 12, 14 inches of rain in 12 hours. Some places got as much as 40 inches of rain. Whoa. Well, why weren't you carrying your umbrellas around a couple of days ago? Well, maybe to keep the sun off of me, but there sure wasn't any rain, was there? Just because there's rain in one location doesn't mean it's going to impact another location. Same thing here. Just because there's a discontinuity at x equals 2 doesn't mean there's a problem at x equals -4. Third potential problem is if you have a vertical asymptote. With a vertical asymptote, what's going to wind up happening is you have some kind of an equation and it's approaching either infinity or negative infinity, and whichever it is, do you buy? Oh, let's call this the point x equals 4. Sorry about that, it's changing colors. At x equals 4, there's a vertical asymptote, isn't there? How would you draw a tangent line? Well, it depends if you're coming in from the left or the right, doesn't it? It's going two different... Oh, wait a minute. If there's a vertical asymptote, do the limits from the left and the right equal each other? From the left, this one's going to infinity, and from the right, it's going to negative infinity. Your left and your right limits are not equal, and as soon as they're not equal, boom, you're done. It's game over. Walk away. Does that make sense to everybody? Okay. On the quiz coming up Friday, I did not do it last Friday on purpose because I didn't want to beat you up too soon with this stuff. I want to make sure that this is working really well and you're really going to be successful with this. But on Friday's quiz, oh, that's right, he's got a quiz there. Yeah, it's up here, it's graded. I got going, forgot to give it back. We'll get it back to you. Okay? Real fair question is something like using the definition of a derivative. Compute. Now I'm going to throw a new notation in on you here, and it's one we're going to use all year. It's easy to overlook, so you've got to develop a keen eye for what's going on in math because the symbols are going to be very small, and if you read fast, you can skim right over it and completely miss the major part of the problem. Compute the derivative of f. See the little hash mark there? The little apostrophe? That means derivative when f of x equals, and now let's do something like 3x squared plus 6x minus 2. Real fair question. Now, probably today, we're going to get into the shortcut methods, and some of you who had calculus in high school or somewhere else already know that the derivative of that is 6x plus 6, right? I mean, you can look at it and write it down. Remember I said there's still going to be problems that you can just do them in a couple of seconds? Okay? You can look at that once you know the secret. And just write down the derivative. Boom, just that fast. However, I'm going to be very careful on Friday and test 1, and we'll talk about that here this week. You'll get to vote on when it's going to be. On test 1, I am going to specifically say using the definition of a derivative. That'll be question number 1 on the test, worth about 10 points. I just gave you a hint of what one of the test questions are going to be, didn't I? Whoa, about 10 more points. That's a whole letter grade, isn't it? So if you figure, I don't really need to study this, there goes 10 points, you're down to a B before you even get started on the test. Or, if you study this, your test grade just went up a whole letter grade, didn't it? A whole letter grade. Okay, so we want to compute the derivative when we're given that particular function. This notation here was developed by Leibniz, a mathematician, 1700s. Calculus was over 150 years in the making by some of the greatest minds who have ever lived, period, in the history of Earth. So this year, when it feels like it's coming fast, it is. You're getting 150 years worth of math in 8 months. Okay? So hold on tight. Okay. How do you do the derivative? Well, the derivative is going to be, and notice I'm going to use the derivative is the limit as h goes to 0, and you know where this is going right here, don't you? F of x plus h minus f of x over h. This one's going to be slightly more involved than the other ones, just because the function's a little longer. We've done it with things like x squared and square root of x and that kind of stuff. But how do you do it with something longer like this? Well, you play the game exactly the same. We do the limit as h goes to 0. I'm going to use a longer line. I don't know how long it has to be, but I'll save some space here. I know there's going to be an h in the denominator. The first thing we do here is we deal with this term. That means we copy down whatever our function is. Okay, I'm just going to copy down whatever the function is. It's 3 times something or other squared plus 6 times that same something or other minus 2. And I'm going to put it in brackets so we can see that that's the function. Does everybody understand what I just did? In the definition of the derivative, in the term highlighted in yellow, it says f evaluated at x plus h. So the first thing I did is I copied down what f is. And now what are we going to plug spaces. X plus h. How do I know it's x plus h? Because it says inside the parentheses there, we're going to put an x plus h wherever there are parentheses. Does that make sense? Minus. Now be really careful. People flub this up, and I'm going to flub it up on purpose. Then it says copy down whatever f at x is. Well, okay, that means copy down our function again. That's this thing. 3 times something or other squared, 6 times something or other minus 2. We know it's subtraction because we're using the definition of derivative. Right there it says subtract, and there's my subtraction sign. What's wrong with that? Well, you got to plug in whatever goes in. It says inside of the parentheses we're going to put an x. It's still flubbed up. What's the problem here? Yeah, we want to subtract the whole thing, not just the 3x squared. So to ensure that you're subtracting the whole thing, make sure that you put brackets around the whole thing. That is the most common mistake year after year after year. Don't be one of the people to join that club. Does that make sense? Equals. Remember, on the left-hand side of the equal sign is still f prime of x, isn't it? So what this is saying is the equation of the slope equals, and all this stuff we're going through, we've got this limit as h goes to 0. It's going to get a little longer. Inside the first brackets, we have 3 times x plus h, the sum squared. Well, that means FOIL x plus h times x plus h, doesn't it? So that's going to give you the x squared, 2xh plus h squared. All I did was I squared x plus h. Everybody good with that? Then, so this piece here is that chunk. Don't want anybody to get lost on this. Plus the next chunk is this. What that's going to look like is whatever goes in here. Well, that's 6 times x plus h, which simplifies to be what? Maybe something like 6x plus 6h, distribute the 6. So we have 6x plus 6h. Does that make sense to everybody? All I did was in that term that's highlighted in blue, it says 6 times x plus h. Just distribute the 6. 6 times x plus 6 times h. Then the last part of this is going to be the minus 2. Okay. And that comes from right there. All of that goes into a parentheses, or a bracket, sorry, goes into a bracket. Is anybody lost there? Does that make sense? Yes, sir.
Why wouldn't you distribute the first 3?
We will. I'm doing this in slow motion on this one. You're absolutely right. It's going to become 3x squared plus 6xh plus 3h squared. But I didn't want people saying, where does 6 come from? So, yeah, you're on it. Okay, now we turn to the right end of that numerator, and you see that minus sign? We have to distribute that, don't we? That thing is going to be times the 3x squared times the 6h and times the negative 2, which will give us minus 3x squared minus 6 plus 2. Everybody good so far? Equals. Now, yeah, we're going to deal with that 3. And yes, you have to keep up with this limit as h goes to 0 part. And what we're going to wind up with is a 3x squared, 6xh, 3h squared, 6x, 6h, minus 2 minus 3x squared minus 6x plus 2. Okay? And I'll get rid of this bracket now. We don't really need that at this point. Everybody okay? At this point, we can start cleaning things up, which is, for a lot of folks, good news. In the numerator, do you see two terms that are combined? There's a variety that'll combine. What's one of them? You see the 3x squared? Yeah. There's a 3x squared at the lead and a minus 3x squared toward the end. Guess what they do? Cancel out, don't they? Yahoo! There's a 6x. See the 6x just above the h? Oh wow, check it out. And there's a minus 6x later on. There's a minus 2 and a plus 2. Well, that kind of cleans things up a little bit. And that gives us, remember on the left side it's still f prime equals the limit as h goes to 0. Don't need to draw a line quite so long now. 6xh 3h squared plus 6h. Can we plug in the 0 value for h yet? We're getting close, but we can't do it just yet. What would happen if you plugged in 0 for h right now? See that denominator? Is a 0 in the denominator a good thing or a problem? It's a problem, isn't it? Okay, so we got to work a little further on this. Okay, that means we have to drag along the to-do list. The limit is h goes to 0. In the numerator, every term has a factor of what? H, doesn't it? So you can factor out that h, and you can rewrite the numerator as 6x plus 3h plus 6. But the cool thing of factoring out that h in the numerator is now the h in the numerator, it's times everything, can cancel with the h in the denominator. Which is really good news, because now we have the limit as h goes to 0 of 6x plus 3h plus 6. And is it acceptable to plug in 0 for h at this stage of the game? It is. And when you plug in 0 for h, what's left? 6x plus 6. Ta-da, there's your answer. Well, what is it? It's the derivative. Remember, the left-hand side is still that f prime stuff. This tells you that the formula for the slope is 6x plus 6. If you look at the graph of this thing, it's going to do something like, I don't know, maybe something like that. But at any location where you want a tangent, the way you get the slope at that tangent is you use that formula 6x plus 6. So if we want the slope at x equals negative 1, what is the slope at x equals negative 1? 0. Oh wow, x equals negative 1 is a maximum or a minimum point, isn't it? Okay, let's go back and look at our original function. Here it is in the upper right corner. I don't want that. It's a parabola. Everybody buy that? Does it open up or down? Up. Now be careful. If it opens up, does it have a max or a min? It has a minimum. The minimum occurs at x equals negative 1. Does that make sense to everybody? Well, Well, gosh, Chuck, couldn't we have just gotten our calculators out and graphed it and figured it out? Yeah, I'll race you. Get your calculator out, graph it, and find a min point. And I know that y prime is 6x plus 6, x equals -1. I'm there. How are you doing? You haven't got your calculator turned on yet, do you? Whoa, this is a whole lot faster, isn't it? And in the business world, time is what? Money. Just save somebody a chunk of money. 5 minutes later, you'd have it all graphed because you'd have to tweak the window and then figure out how to calculate the max and the min. And I'm done. I'm on to the next project. This stuff is way fast once you get the hang of it. I mean, it is really cool how fast it is. That's why it's caught on over the last couple of 100 years and it hasn't gone away. This stuff is really useful. Are you okay? Now, one of the things that wound up happening back in the good old days, like 150 years ago, if they wanted to figure out where the slope was 0, they'd use this definition. And they'd go through all of this stuff every time they needed to do something. Well, after a while, they started to notice something, like if y equals 3x squared plus 6x minus 2, y prime is 6x plus 6. If y equals a negative 2x cubed minus 9x squared plus 18, how would you like to do something where you're cubing the x plus h? That's going to take a little while, isn't it? Well, they happen to notice, oops, don't want that to disappear, the derivative is going to be a minus 6x squared minus 18x. Give me some kind of a polynomial. I don't want you to think I've got this rigged or anything. Give me some kind of a polynomial. You can't be wrong. You can use any power of x you want, any coefficient you want. You going to be brave and daring, Jake? Nah, not so much. Okay, somebody tell me your age. Gentlemen, never ask a lady her age. Guys, what's one of your age? 20. Okay, so we're going to do 20. X to the 5. Plus or minus? Plus. Give me another number. 18. X, thank you. X. 4. Plus or minus? Minus. We'll do this one more term. 200. That's fine. Go get them. Yeah, that's it. Let's live big. X to the 2. How many of you want to use the definition of a derivative to compute that baby? Well, you're going to have to do x plus h to the 5th power, aren't you? Yeah, well, while you're doing that, I'm going to go ahead and jot down that it's 100x to the 4th, 72x cubed, minus 400x. You got that done with the definition yet? How you doing with your x plus h to the 5th power? Chuck, I barely got it written down. There's got to be a better way to do this, right? And they started noticing patterns. Are you noticing the pattern? Some of you already know the secret pattern, right? What's the quick way to do these derivatives? It's okay. You can spill the beans. When I was in calculus, we were required to continue using the definition of the derivative until we figured it out on our own. The prof just said, pointed this out and left. That was the end of class. He said, you will keep doing it this way until you figure out some easy way on your own. And he left. Whoa, you think we were inspired to find an easy way? Actually, it was kind of fun. It's kind of funny. What's the secret? Yeah. That's right. Yeah, you got it. Way to go. So if we have something like k of x equals 4x to the 30th, how would you like to do that times itself 30 times on x plus h? Well, yeah, that'd take a little while. Minus 12x to the 5th plus 17x minus 8. The derivative to this is computed by, you take whatever the exponent is times the coefficient. 4 times 30 is 120, x2. Then what you do is whatever the exponent is, you subtract 1. 30 minus 1 is 29, isn't it? Minus. We're going to play the same game here. We're going to take the exponent times whatever the coefficient is. 12 times 5? 60. X, you subtract 1 from whatever the exponent is, 4. Plus, see that 17x? What is the exponent on the x? 1. Yeah. So we're going to take the 1 times 17, which is going to give us 17, and we're going to get x to the what power? 0. Okay, here's one for you. Any number raised to the 0 power is what? 1. Oh, so this is 17 times 1, right? Because it doesn't matter what x is. When you raise it to the 0 power, it's going to turn into 1. So this becomes 17. Well, I'm just going to write it like that then. This next term, the minus 8, is really 8x to the 0 power, because it's really 8 times 1, isn't it? When you take that exponent and multiply it by the minus 8, what do you get for a coefficient now? 0. You mean that term goes away? Yes, it does. It doesn't go away. It's really plus 0. But realistically, are we going to keep writing plus 0 all year? I don't know about you, I'm not. Help yourself. You can do it either way you want. Whoa. You mean to tell me that's all there is to doing a derivative? You mean to tell me we've been doing, look at this, it won't even fit on one screen. It takes about a screen and a half or two. This definition of a derivative stuff, all of this goings on, and goings on is nothing more than just look at the answer and write it down. Yep. They noticed it pretty quickly. It wasn't like they spent 50 years doing definitions of derivatives. Now, the cool thing about this is you don't have to, hey, when we slid into this, we got into section 1.5. I don't know if you noticed it felt like a new section or not, but if you're thinking this feels like a new section, it is. The cool thing about this is if you have something like j of x equals the cube root of x to the 5th power minus 17x plus the square root of 6. And you're asked to compute the equation of the tangent line at x equals 1. Well, to compute the equation of the tangent line, the first thing you have to compute is and it begins with an S, L, O, the slope. You got it. When you got to do the equation of a tangent line, any line, one of the things you need for a line is its slope. Well, we all know the code word for slope in here begins with a D, derivative. That's right. Okay? So when people are asking you, what are you doing? Don't say, we're getting slopes of lines, because they're going to say, I was doing that in 8th grade. We're computing derivatives. Ooh, I don't know what a derivative is. It sounds better. Okay, So the first step in doing this, number one, is get the slope. Now, that means we're going to need to compute the derivative of that function, doesn't it? Well, gosh, Chuck, I don't know how to do the derivative of the cube root of x to the fifth. Well, as soon as you use some of your algebra to rewrite that, in fact, we can rewrite that as x to the 5/3. Does that make sense that that's x to the 5/3 power? Oh, wow. As soon as you know that's x to the 5/3 power, you can crank out the derivative just about as fast as you can write it down. Because what's the coefficient going to be on the first term? Well, it's going to be 5/3 x, because remember, this exponent comes down, right? It's going to be 5/3 x to the, what's 5/3 minus 1? 2/3. 5/3 x to the 2/3 minus, what's the derivative of the next term? Well, let's see, the exponent on it is a 1, so we're going to have a negative 17 times 1 is a negative 17, and it's going to be x to the what power? 0. And anything to the 0 power is 1. That's just going to be minus 17 plus, what's the derivative of the square root of 6? 0. Because that's really the square root of 6 times 1, isn't it? And another way to write 1 is x to the 0. Oh, yeah, I guess I could have written it like that. And then the 0 from the exponent comes down times square root of 6. And what's 0 times square root of 6? 0. And then it doesn't matter what else you have in the way of x. Anything times 0 is 0. So the derivative is that. Now, last week I made mention, and it may have just slid on by, I made mention you've got to start being extremely careful to label every equation you have, because you're going to start getting several equations laying around. We have our derivative, which is right here. We have our original function, which I'm going to write as x to the 5/3 minus 17x plus the square root of 6. Okay? What we need to do now is to get the equation of a tangent line at x equals 1. Well, the equation of a line is y equals mx plus b. Does everybody buy that? Well, we need a couple of things. We know what x equals. What does x equal in this equation? 1. So we're going to have, we need something for y equals, we need something for the slope, we know the x value, and we're going to have to compute what b equals. Here's where you got to be careful. You get the equations mixed up, you'll get your numbers mixed up. Where do we go to get the value of y? Which equation do we use to get the value of y? The original. The original is going to give us our y value. Does that make sense to everybody? So you got to keep them labeled. When we plug, well, how are we going to get a value for y out of that? You just plug in x equals 1, don't you? And what's 1 to the 5/3 power? 1. Well, that part's not too bad. 17, the minus 17 times 1 is minus 17 plus the square root of 6. Yeah, that's not so pretty. So for the moment, I'm going to put minus 17 plus the square root of 6. That is the y value. That's a number, isn't it? No, Chuck, that's a mess. Yes, ma'am. I'm sorry? Oh, you're right. Thank you. I skipped the 1. Way to go. Yes, you're absolutely right. It's a minus 16. Way to go. how upset I get when people point out I made a mistake? I'm thrilled because it means two things. One, you know what's going on. Two, everybody else isn't going to be trying to figure out how to get minus 17. Okay? Now, we need a slope. Where are you going to go shopping for slopes? This one is your slope. See it? Oh, it's already labeled. Slope. What value do you plug in for x there? 1. Yeah, we're going to use the x value as 1. And you're going to get a 5/3 out because when you plug 1 in there, 1 to the 2/3 power is 1 times 5/3 is 5/3. So this is going to then give us 5/3 minus 51/3. Whoa, wait a minute. Where'd you get 51/3, John? Where'd the 51/3 come from? 17 with a common denominator, isn't it? Okay, so that's going to give us then 5 minus 51 is a negative 46 over 3. I would encourage you at this point to run to your nearest calculator to solve for b. Use 3 digits after the decimal, and that'll give you a b value, won't it? And what you'll wind up with for your equation of the tangent line is y is equal to a negative 46 over 3x plus whatever mess you get for b. You can solve this equation right here. You can solve for b, can't you? That's just real straightforward algebra. That then gives you an equation of the tangent line. But Chuck, those numbers are ugly. Yeah, welcome to the real world. Okay. Sometimes we're going to have numbers like 1, 2, 3, negative 5. And just as frequently, we're going to have things like minus 16 plus square root of 6. And that's just as good of a number as 4. Okay. At the university, they talk about diversity and inclusion. Well, we're including radicals and stuff. Okay? Hey, does this make sense? You know what? We covered how many sections today? 2. 1.4 and 1.5. Okay? Folks, I'll see you all Wednesday. I hope you have a good day.